Good morning, everyone. Good Friday morning, April 15th here, ready for our next Eastern Region Science Sharing webinar. This morning, we have Justin Arnott from the Gray main office and Rodney Chai from the Boston office this morning to speak with us about using high-resolution ensembles in warm season heavy precipitation events. So without further ado, Justin, Rodney, the floor is yours. Thanks.
Wonderful. Thank you very much, Jordan, and good morning, everybody. And just happy Good Friday to everyone today. It's beautiful out here in Maine. We're excited. It was 45 and drizzle yesterday, so we're always happy to see the sun, especially in the month of April. So we're going to talk to you, Rodney and I are going to talk to you today about really kind of where the rubber meets the road in terms of high resolution ensembles and using them for what is a very difficult and challenging problem, which is warm season QPF. I want to start by saying that this was not just work that Rodney and I did. This is essentially a COVID project. CSTAR 7 kind of spun up, and I don't know, I think, Rodney, we had our first team meeting sometime in February of 2020. And so we all know what happened shortly after that. But this is a team effort between 3 offices, Boston, Caribou, and Gray. And I've listed the other team members here who've contributed. And really the goal in this CSTAR project was to, and this was a kind of one of the, Mike Evans would know the name, the collaborative projects where we don't have to actually have a student working with us. This is all Weather Service. But we're looking at warm season QPF. It's a huge challenge in the model guidance, and we have all these great new tools, and we all know and we love things like the href, or we think back a couple of years to the NCAR ensemble. But how do we use them? How do we leverage them most effectively? And that's really that was our goal here. That was what we were trying to get out of this project is. Can we give forecasters any insight on how to best interact with these new tools instead of, or in addition to just saying, wow, these are great, I'm just going to start using them. I wanted to also acknowledge a couple or some help that we had. The NCAR folks with the ensemble, their forecast was terrific. And then specifically Bert Roberts at SPC hooked us up with a lot of the href data, just the detailed information. You can imagine it was a little bit of a Herculean effort to move some of those files just because of the size of those ensemble, so given their resolution. So we're very appreciative to some of the data that was made available to us for this project. So methodology, this is how we're going to go through. The presentation essentially is going to step through our methodology that we did in this project. We gathered, observed heavy rainfall events over the past roughly 5 years. We'll show those in detail shortly. We gathered headlines from the Weather Service during that period. Then we went to the ensemble information itself. We gathered it. We then compared it to what was observed in terms of kind of a bulk verification study. And then once we had some basic information from that, we turned this to a case study analysis where we examined a number of case studies, all of them independent from the original analysis. So all of them just happening in the past couple of years. Given that this project kind of evolved over the course of the last 2 years, we had quite a bit of weather happen while we were doing this that was not in our original data set. And so that gave us a good independent data set to work with, including some neat events even last summer. So to gather the events, we went back over the past 5 years, 2015 to 2019, which would have obviously ended just before the start of this project. And our data set to look at observed precipitation was NCEP stage 4. And one of the first ways we did this was more semi-subjectively, was to actually do a visible search for areas of 1 inch, 2 inch, or 3 inches of rainfall in 24 hours. And we looked for that over the area of an average New England county, which is roughly 1,000 miles square, which I have Merrimack County, New Hampshire outlined on this map, and that happens to be just under 1,000 square miles. And so, and the reason for that was we weren't going to attempt to have the models or the ensembles try to pinpoint some really highly localized event. We wanted something with some scale to it. And so we did that visibly. So we kind of looked for areas that were that size, and we see in the map that's shown here, no doubt that this passed the test, at least at the 1 inch threshold, and it was getting close there on the 2 inch threshold. And then we supplemented this with GIS-based analysis using the Gazpacho package, which was developed in other parts of the Eastern region and used most frequently for some of our snow analysis, but we used it after the fact to kind of verify and also just plot and look at some of these observed events. And so this formed, as you can imagine, a big spreadsheet of different variables. Did we hit the thresholds of 1, 2, and 3 inches? And then we did have the dates there to the left. So just a screenshot of that on the bottom here. And I'm not going to spend too long on the climatology, but just some basic just facts that we've seen. And this is over New England, that we had roughly just over 20 events per warm season, which equates to maybe about 1 per week over the course of the study period. We had 18 2-inch events over the time frame, which is 3 to 4 per warm season, or maybe getting close to 1 per month. And then we only had a couple of 3-inch events, and so that shows you that they're not even an annual occurrence. That's again a 3-inch event on the scale on 1,000 square mile area. And what I've included here on the bottom is just a little bit of the climatology over the course of the year. As you can imagine, they're kind of centered in the middle of the warm season for us in New England, with July having the most 1-inch events. And then for year by year, you can see roughly between 20 and 30 events per warm season, bouncing around a little bit, but of course nothing long enough that we could make any inference about trends or anything. But we can certainly see the peak in the middle of the summer. I've done the same here with 1 inch across the top and 2 inch across the bottom. And so the plots across the top are exactly what you saw on the last slide, and I just added the 2 inch ones. And what you can see is September tends to stick out for the 2 inch events, and there's 2 reasons likely for this. Clearly, as some of you are probably guessing, at the tropical influence, which wasn't honestly all that great in 2015 to 2019 over the Northeast, but there was an event or two that snuck in there, so we didn't try to filter those out. Another thing is that just September becomes much more synoptically forced, and so you tend to have with convection interacting then with more synoptic scale systems, you can spread those higher precipitation amounts frequently over larger areas, and so when they do happen, they can be substantial. And again, I'm not going to try to make any real inferences from the yearly information, but you can see for 2 inches, you might have 6, 7, 8 events in a year, or you might have a year that you have barely any. So just to be aware of what we were looking at the ensembles to try to reproduce, and how many events we're looking at here. Clearly, with a 5-year case set of cases, we're only going to be able to draw, the higher the threshold, the less we're going to be able to draw out of this, just because of the few cases that we have to work with. So step 2 was to move on to Weather Service headlines, and we essentially grabbed all of the warm season hydro headlines for this period from any office that included portions of New England. So that's whether it be Norton, Albany, Upton, Burlington, us in Gray, or up in Caribou. And we just all hydro, flood watch, flood warning, flash flood watch, and flash flood warning. And we were looking at non-river products. And so just to get a feel for, in these events, 1, what happened, 2, what did the ensembles think was going to happen, and then 3, what did we think was going to happen? More of a watch idea, or warnings. What were we responding to? And there's obviously a lot more flash flood warnings than other products issued, and that's just the nature of them, and not so much a trend here. And then in terms of when they were issued, they similarly tended to follow kind of what we saw for the 1 and 2 inch climatologies, or especially the 1 inch climatology, with a peak in July, and more for the second half of the or middle to second half of the summer than the first half. So, but we just kind of catalog these for kind of saving for later use, and we'll get back into how we actually applied these in a little bit. So now let's grab the forecast events. Now it's time to actually go to the ensembles. It took this stage of the process it was a little bit later where we actually started to go into this, where we grabbed data from both the NCAR ensemble for 2016 and 2017, and then version 2 of the HREF for 2018 and 2019. And we decided to approach this in two different ways. One was objective and one was, I'm going to call semi-subjective. So let's describe them a little bit. The objective case is pretty straightforward. You look at what the observed group, what the observed cases were, and you examined how the two ensemble systems performed for those days. You looked at very bulk statistic, mean absolute error, bias, things like that. And you get a very quantitative number for those events, and you do an area wide. Let's see how these ensembles did in terms of how they forecasted for the entire area. Now, independently from that, we looked at the performance of these two from a more of a subjective, or what I'd like to say is kind of from the eyes of the forecaster, where the forecaster who was gathering this information did a visible search for these events, and came up with over 120 of them within the ensembles, and then compared them with what happened, as well as what we were issuing in terms of headlines. So one was done purely kind of from a software side of things. We have the observed events. Let's plug and chug on the statistics, and the other was kind of put it through the eyes of the forecaster to say, identify an event, identify how the model did, see which one did the best, and then just start cataloging results. And so you're going to see less in terms of specific bias numbers and mean absolute error numbers, you'll see it more in terms of hits and misses. And to answer your question, Jeff, to identify them, you're looking. We're gonna tend to look at means, probability match means, and the max are going to be the variables. So it's not going to be single members, although those single members hitting an event somewhere might play a role. And so it's more on the bulk scale. It's more the looking at them all together, but looking at them all together in different variables that are available to the forecaster. So from the objective side of things, we looked through HREF cases from 1819, and then even threw in some from 2021, and then some NCAR ensemble cases as well. And those were analyzed using ArcGIS. The ensemble QPF data was converted to TIFFs and math done, raster math, to compute the biases and the error. We then there was another portion of the analysis where we looked for, did we capture what the max observed QPF in the domain with the ensemble max or with the ensemble 95th percentile? Now, if you've been on the HREF ensemble page, you're going to see that the 95th percentile isn't something that you can go quickly get. But given that we had the data itself, we were able to compute that and actually look at it to say, well, there's at least a guess that maybe the max would be too hot. And so maybe the 95th percentile would be a better way to go. And it was just a hypothesis and a thought that we examined. And so we looked at 63 cases to review whether we were able to capture that max, or whether we overshot it, or whether we came far short of it. So that's the basic idea there. So let's look at the first question and answer here. So what parameter is the single most reliable for grids and large forecast areas? And you're probably knowing or thinking what I'm going to say here is probably, and it's intuitive. What I've shown here is in terms of the maximum, the mean, so the ensemble max, the ensemble mean, and the probability match mean, which case had the least bias and which case had the least overall error. And as you would expect over the course of longer time frames, the mean is the most reliable. It has the least bias in most cases, and it has the least error in most cases. But you can also see that the probability matched mean gives you a bump up over the max. The max is not what you're going to be using. If you're taking the ensemble max and putting it into your grids for a forecast, you're going to have a high bias, a serious high bias. And so we'll get into where you actually can use the max, but you just can't use it as a gridded solution. But you can see the probability match mean, there may be some cases where it actually comes into use. We didn't find a lot of difference between, there were some stratiform events in our database. It wasn't all convective. There wasn't a big difference there. But the probability match mean did perform better in the couple of tropical events that were actually sampled over the 5-year period. And so you can get the first kind of nugget there, which is the mean is probably the first place to start in terms of a gridded forecast. The next question is about the max and how to capture the highest value in the domain. If I want situational awareness on what is possible today, the question we posed was the highest max or the highest 95th percentile value over a region a good situational awareness tool for a reasonable worst case scenario, which would be, in this case, localized flash flood potential. Now, it's going to take me a second to describe this, but the probability of detection of the highest value in the domain is shown in the first column. And so you can see that 95% of the time, the ensemble max captures the observed max. 80% of the time, the 95th percentile captures the obs max. So clearly the probability of detection is a little less for the 95th percentile, as you'd expect. But the question that's not being answered there is, well, does it like exceed it? Is it like double the max? And so it's not very useful to us. And that's what we'll try to peel out next. So the middle column is the average exceedance, and how much did those two variables, the max and the 95th percentile, exceed the max in the domain. And so you can see the max exceeds the max in the domain by an average of almost 80%. So that's a pretty substantial overestimate. And then you can see this 95th confidence interval in terms of it always overdoes the max pretty much. Whereas the 95th percentile only overdoes it by about 40%. And you can see the confidence interval there. And then the final column, which is maybe just adds a little bit of detail to this, is kind of think of it as this: 80% of the time, those two variables, either the max or the 95th percentile, fall within the above interval. So, for example, the max, the ensemble max, 80% of the time, it's going to fall between 4% over the max in the domain that's observed, or 160% of what's in the domain. So it's always overestimating. Whereas the 95th percentile, 80% of the time, falls between 20% below what is actually going to be observed in the domain, or 100%, so a double of what's in the domain. So what this is telling us is that, the 95th, to answer our question, the 95th percentile is a pretty reasonable indicator, but these bounds are huge. I mean, there's like 100% width there, right? And so there's pretty high case-to-case variability. Hopefully, once we have a decade of or more of these data under our belt, we can maybe refine this some. But it shows that it may help us, at the sacrificing of having a few events that might be slightly underestimated. It might help us with the problem of the max sometimes just completely overdoing things and really putting us in a position to be with a serious high bias in our, if not in our grids, at least in our mental expectations, and maybe drawing headlines and things like that. So that's just one of the things that we analyze, because this might be a parameter that we could actually ask for and say, you know what, this is more valuable to us, the 95th percentile, at least in addition to the max, if not instead of the max. All right, let's move on to the next step, which is our semi-subjective bulk verification. And this is where we identified the days, again, producing 1, 2, and 3 inches of rainfall, and then we do hit and miss statistics. And hit and miss statistics are whether looking at a 3-hourly forecast, a 6-hourly forecast, or a full 24-hour forecast. And we also look at how the Weather Service hydro products worked on that day. And we essentially, the boiled down result are a set of 2x2 contingency tables for POD and FAR. And the main thing, it's not going to be, as I go through the next set of slides here with the results, don't pay attention to so much what's in the 2x2s, because it's the POD and FAR, which is going to be kind of our curiosity here, what we're going for. So let's just look first at how the href ensemble versus the NCAR ensemble did for 6-hour forecasts of an inch at an inch threshold. And I'm going to direct you to the bottom there where you see POD and FAR. A couple things are going to jump out to you, and it's going to be a theme, a consistent theme. The href, you're like, wow, like no false alarms. That's pretty awesome for an inch in 6 hours. I'm kind of impressed at that. I'm a little bit surprised by that, but I also miss more than half of them. So that's not good. The NCAR ensemble hits many more of them with a POD of 0.7, but the FAR obviously comes up. And so it's probably an overall better situational awareness tool back. The NCAR data was during the years that we verified it. The CSI comes out a little bit higher, and you miss fewer events with a, not an unreasonable FAR. Now that's at an inch. Let's move up to 2 inches. And now you're going to see the CSIs both come down. They're actually both the same, but the same kind of error statistics, except for now the href starts to have false alarms, and the POD is significantly less. So this is the classic. POD is less, FAR is not quite as high. For the NCAR, the POD is higher, but the false alarm rate's also higher. And so you're quickly losing skill in both at the 2-inch threshold, but you can still capture events. And I think that's going to be one of the take homes today, is that these tools can allow you to be ready for the potential for the event. Their error statistics aren't great, but in terms of being prepared and then adding things to this to help refine where you think these heavy events occur will be important. Now let's go up to 3 inches and just be aware there are not many observed cases, but unfortunately there are quite a few forecasted cases. And so you see huge false alarms, not very, yes, the PODs may be high, but there aren't that many events. And so we're forecasting events that aren't occurring, and you can't really say that there's much skill here if you say there's going to be 3 inches every day and then once a week there is. But I would just caveat here is there's not a lot of cases to work with at 3 inches. And so, but the false alarm thing comes through, and we got to be cognizant of that. All right, let's switch over to the probability matched mean and look at probability matched mean 24-hour forecasts of 2 inches. So I'm only giving you just a scattering of some of the things different things we looked at. We could be here all day looking at all the different combinations. But you can see for a 2-inch 24-hour forecast, the probability matched mean has a lot of missed events. PODs are only are below 0.4, so you're missing 2/3 of the events. You don't have a lot of false alarms, but you're having a lot of misses, and probably somewhat superior for performance here from the href probability matched mean, just because of the fact that it has fewer false alarms. And so at 2 inches, you've got some skill, but not a lot. Another way to look at it is to compare how the max does versus the probability matched means. I've got the PMM probability matched mean on the left and the max on the right. Clearly, you'd expect the max to have a higher POD for 2 inches in 24 hours, and it does. 64 versus 39. But the FAR, it comes at a cost of a higher FAR, and in the end, it's a wash in terms of your overall skill. But it depends on what you're looking for, right? And we're going to kind of continue with that story that the max is going to help you from having the back of your head what's possible today. I put the mean in my grids, and now I need to use the other tools to help get me to the right forecast and the right warning strategy or watch and warning strategy for hydro products. Now, let's take a look. This is no longer using QPF or what was observed precipitation-wise to verify. This is looking at what is the 2-inch. So if we look at the forecast of 2 inches from either from the max from the HREF, and we compare it to whether an eventual flash flood watch or flash flood warning was issued from the Weather Service. What's the correlation there? And so it shows that what's interesting is that the forecasts here only had a probability detection of less than 50%. So says that the 2-inch signal misses more than half of the days in which we actually end up issuing or had issued a flash flood watch or a flash flood warning. And so there's some missing information here to draw all the dots together. You could also have flash flood watches that ended up being false alarms themselves. But in terms of flash flood warnings, we're seeing precipitation. We don't tend to issue those without seeing anything. And so it's suggesting that there are still a significant amount of missed events at the 2-inch threshold from the HREF max forecast, in placing it in a particular 6-hour period. And so that may argue that you need to broaden your time frame out to something more like 24 hours to improve your situational awareness for events. And I can do the same thing for the NCAR. I'm not going to spend much time here, but the basic difference was the NCAR was a hotter ensemble. It just had the PODs better, but the FAR is higher, and so the CSI is still not good. And so it missed a decent number of events, but it also false alarmed a lot. And so that's just a underlying attribute of that ensemble case. So I'm going to hand it over to Rodney here now to dig in a little bit to the individual case studies that we looked at after the bulk verification. Go for it, Rodney.
Well, thank you so much, Justin, and thank you so much to everyone for attending this morning. And we're going to look at 3 case studies of where the HREF has been put into use to forecast potential flash flooding, and we're going to see how it has performed. And we're going to go through actually 2 non-tropical events and 1 tropical event, Hurricane Elsa. And so the first event would be the Down East Maine flash flooding. So that's actually in Caribou's area. And so you can see there's what you're looking at is the 24 MRMS flash QPE return period, and you see that there are 2 bullseye over Bar Harbor and Jonesboro, and you're looking at basically 75 to actually over 100 year return period. So that's actually a very significant flash flooding event. You can see on the left-hand side some of the reports. Bar Harbor and Jonesboro are receiving over 5 inches of rain, and that's from, if you look at the surface analysis on June 9, there's basically a stored boundary set up it stretches over from basically interior northern New England all the way into Down East Maine. And here's a reflectivity at the lowest altitude loop from MRMS, and you can see there's some kind of like back building over the area that I just mentioned, and that led to the 5-inch rainfall total and the flash flooding. And here's a look at the precipitation estimate in the 12-hour period, and you can see again showing how really 5-inch rainfall across Down East Maine. And here's the 12-hour recurrence interval. Again, that's for the 6-hour period. All right, so let's take a look at the HREF performance then. And this is from the 0Z simulation, 6-hour lead time. So admittedly, from a forecasting standpoint, this is kind of a little late in the game because by that time, 0Z, you would really have been, it's really game time, and that's the DSS would have been done, and this is really kind of like more of like meso analysis and situational awareness time. But let's take a look at the 0Z simulation. You can see starting on the left-hand side, you have the 24-hour mean, and then going to the right, you have the 24-hour max, and then followed by the probability match mean and then the LPMM. So you can see that the mean is kind of, I mean, obviously that's kind of like an underdone situation. For the mean, I mean, it's only showing down East Maine having, an inch of rain or maybe 1.5 inches. And then you see the max. It really kind of, capture the upper end of this event very well. You can see that 4-inch, 5-inch total. Not exactly over the same location, but it kind of gives you an idea what is the upper bounds of this event, what the potential, what is the reasonably worst case scenario for this event, even though the location is not quite right. And then the probability match mean, and just a reminder, probability match mean combines the ensemble mean, but then it also preserves the amplitude of the individual members. So in this case, it's kind of like a more skillful version of the ensemble mean. And you can see, it's kind of like in between the mean and the max in terms of performance, and then the LPMM again, pretty similar to the PMM, but a little bit more robust in terms of the precipitation estimate. All right, so it really to reinforce some of the points I've talked about again. The mean was the best for all parameters and the CWAs, except for the area across Caribou area, in this case down East Maine, where the PMM was the best. And comparing, so I've talked about the 0Z href, and that's really at that time the game has already started, so it's again it's not so really the best, the most the forecast that the forecasters really referred to was really the 12Z href, which is 18-hour lead time, and in this case the regional max was near the observed max, but misplaced in time and space. So we did not show it here, but the max was actually along the mid coast of Maine during the day. So in this case, this is a nocturnal event. So the max actually was misplaced, not just spatially, but also temporally. So so from and as I would touch on later on in the key summary, for a forecaster takeaway, the max guidance is, I think, is really for good situational awareness. How much can the atmosphere potentially give you? But you still have to use a lot of your forecaster discretion and your meteorology expertise to decide which guidance is the best. It might be a case of one size doesn't fit all. So moving on to the second case study, and this is a tropical case study, Hurricane Elsa, July 2021. And on the left-hand side, you can see the MRMS, 48-hour precipitation estimate. You can see the swath of really 2 to 4 inch totals from pretty much from Long Island all the way to down East Maine. And taking a look at the href performance, 15-hour lead time. So starting with the max, followed by the probability match mean and the mean. And you can see the max clearly is kind of, it's a little bit indiscriminate in terms of showing the 3 to 5 inch rainfall total. The PMM is a little kind of in the middle of the road between the max and the mean. So in terms of summary results, so the regional max, and when we talk about region, this is actually FEMA Region 1, and which is basically the whole of the covers almost the entire Northeast. And so the regional max actually, so comparing the max in the 95th percentile, you can see by the numbers here on the screen that so the 95th percentile, even though it fell short of the observed events by 4%, but it really it kind of drastically reduced the error of the false alarm ratio. So instead of exceeding observation by 69% in the first 24 hours, if you use the 95th percentile, you only exceeded it by 24 hours. So that's quite a bit more skillful than just using the max indiscriminately. And then looking at here at the table, here you have the number of instances where a parameter had the least bias or error over a CWA over the 24-hour period. So you can see that in this case, the probability match mean really just reduces the error, although it does have a pretty good bias. So moving on, so this is case number 3, and this is actually in the Boston Norton office area, and this was June 28, 2020. And so basically this was a kind of like a hybrid event. So initially it was, we were issuing severe thunderstorm warnings, and there was severe convection over Boston. But then it created a cold pool that, combined with the sea breeze boundary to produce an environment conducive for backbuilding storms into northern Rhode Island and Norfolk County, Massachusetts, which is just south of Boston. And in terms of PWAT values, around 1.5 inches. So it's above normal, but not blockbuster. But in this case, the mesoscale environment really just allowed this event to overperform expectations. So in Norwood, Massachusetts, which is about 15 minutes south of Boston, the streets turned into rivers, including Route 1. The Norwood Hospital had to be evacuated. There were reports of over 4 inches of rain in 1 hour. And this was only the 3rd time the Boston office has had to issue a flash flood emergency, and the first for a non-tropical event. The first 2 being Arthur and Irene. Taking a look at the maximum unit stream flow from crest on the left-hand side, and the HP on the right-hand side, you can see just kind of where the heavy rainfall occurred, and you can kind of see actually where you have the blue shading on the right-hand side. That's kind of where Norwood is, and you can see how this is really a cold pool induced event, and then with the enhanced by the sea breeze boundary. So that's why it's so important to have to maintain situational awareness, and have the meso analysts being very focused on identifying the potential boundaries and where it could stall, because that would be kind of the area to really focus on for the potential flash flooding. Taking a look at the crest graph, and on the left-hand side, the hydrophobic graph on the right-hand side. Obviously, the hydrophobic graph, you're going to have a much higher y-axis in terms of unit stream flow. And this is a situation where the hydro person, would have to, based on his or her understanding of the local geography and what kind of surfaces you're talking about. Is it mostly a vegetated area? Is it an area that is highly urbanized? And you would have to decide. Um, you know, even though the hydrophobic, you know, model would tend to have, too much of a bias, but in some cases, it might not be a bad idea to look at the hydrophobic output versus just looking at crests. But in this case, they both depicted that surge around 2021Z for Norwood. So taking a look again at so on the left-hand side, you see the observed / radar estimated rainfall. So the numbers on the screen, that's basically the observed rainfall, and the color shaded part of the plot is the radar estimated rainfall. So in this case, you can see Norwood is in Norfolk County, so you can see the bullseye of the red and purple shading. And some of the reports show Norwood having, over 4 inches of rain, and then just further west, actually almost 5 inches in Bellingham. And then on the right-hand side, you see the 6-hour href ensemble max actually captured the max amount, actually pretty close to Norwood, but although it also showed some other, places that didn't quite get hit as quite as hard. But once again, while the ensemble max is a very low probability, of verification, it is very useful to see what is the goalpost, what is the reasonably worst case scenario. So finally, take home points for forecasters. The ensemble max is really a good situational awareness tool for identifying the reasonable worst case scenario. And using the 95th percentile actually may improve the high bias while not dramatically decreasing the POD. And ensemble max, again, it's it likely is the best variable for the deterministic forecast. It reduces error and bias, but it is not the best to use for a high impact hydro situation for situational awareness. Probability match mean. So overall, it is not a terribly strong assay tool for high impact events, with the possible exception for tropical events, as we showed for the Hurricane Elsa case study. So the key is really when again, you can, especially when giving IDSS, you have to know your audience and their needs, and one size does not fit all. And this is where the meteorologist expertise come into play. You have to decide, what you're going to use the mean, the PMM, or the max. In this case, you can see the max, and this is going back to the Norwood case study. The max helps you identify, what is the high end potential, in this case, 4 inches. And that was what happened in Norwood. And so the mean, you can use it as an area forecast for the grids when you're producing the forecast on GFE, and then ultimately using a combination, you can get a pretty good, middle ground for getting the forecast to be reasonably accurate, but also identifying the high end amount. So, and finally, I want to say it's so important, to have a meso analyst when working, be it a severe event or hydro event or a hybrid event in the case of Norwood. And so I believe this is the end of the presentation, and I'll pass it back to Justin and Jordan.
Yeah, thank you, Rodney. Yep, that is, so I'm going to just leave this slide up as it's kind of the take home, but back to you, Jordan.
All right, Justin, Rodney, thank you so much for your presentation. As a reminder for all those who arrived sometime after the start, this is being recorded, so any questions or comments, both in the chat that will get captured, or questions, now can be discussed now, or if you think of them later, I'm sure they'd be happy to answer them afterwards as well. With that, I guess I'll start with a comment. Not so much a question. I thought it was really great and really informative to talk about, the differences in the HREF versus the NCAR ensembles and the power and looking at 2 and 3 inch events, since that is obviously a situational awareness an issue that can come up a lot, I'd imagine, and that's really important information to have on hand in these situations. So, that was really interesting in terms of being able to set, as you perfectly worded it, the goalposts of how to look at events for situational awareness. So that was really important from my end.
No, I agree that there's importance to understanding your modeling systems. There are different error characteristics for both of those, and that's why we do verification. That's why having some knowledge of the underlying performance of these systems is so important to being able to use them effectively. And that if you know the NCAR ensemble is hotter, then that good. You can use that, leverage that information. So no, I appreciate that, Jordan.
Yep. I'll also add, and Tim, I see your hand is up. I'll also add very quickly that you mentioned there were very few 3-inch events that you had over this time. And hopefully as time moves on, we'll find more to be able to strengthen the results even further to see where this goes.
Absolutely.
Yep. Tim.
Excellent presentation, Justin and Rodney. To follow up on your point, Justin, I really enjoyed seeing the reliability information with respect to the HREF max in terms of setting your goalposts. It was also fascinating to see how wide that variability can be. From your study, do you have at least a qualitative sense of maybe scenarios where the reliability of the HREF max for those totals will be better versus other setups?
I guess I mean, I don't have any numbers to back it up, but just kind of qualitatively, it seems that where you're going to get into trouble is when the HREF, it pinpoints, it gets like back in the Down East Maine scenario, or even in this one, even in the Norwood scenario, you've got all this, little popcorn setup where one ensemble member hit it here, one ensemble member hit it here, and any one of those you're probably gonna eventually in a lot of them you're gonna overdo the QPF, and you may overdo it for anything. Whereas in the ELSA case, you notice that while maybe you could say the max was overdone, it really wasn't overdone by a ton because it was such the forcing was broader. So I think applying a high end from a very isolated event and saying, okay, no, my likelihood of or my high end today is 6 inches because one member had 6 inches in one spot is probably more prone to getting you in trouble than saying, you know what, we got a pretty well synoptically forced event or a tropical event that's given me a high end of 5 inches. I can probably trust that. I think personally, I think I would trust that a little bit more based on what we've seen from the data here.
Yeah, I think Justin and Timothy, I would just chime in here, at least from my experience working hydro events at Boston office. If you just use the max, I mean, you're going to basically over forecast for a lot of places. But what is useful, at least from using the HREF website, you have the option of looking at the individual members, and after all, it is 5 members over 2 time steps. So you have the HER, the NAM 3K, and we in our office we really place a lot of premium on the Nerster-Wolf and the ARW. So we would look at the Nerster-Wolf and ARW to see and compare it to the max. And if the Nerster-Wolf and ARW are showing it as well, then it increases our confidence, and we can also communicate that to the emergency managers that have to keep an extra eye on the hydro situation that may or may not unfold. And from an IDSS standpoint, the EMs always tell us they want to know what is the worst case scenario. So even though if it doesn't happen, at least they at the back of their mind they can prepare if the worst case scenario really happens. So I would say that I think just going kind of looking underneath the hood and seeing what the individual members are showing. And there are certain times when it was clear. I mean, if it's a strong, this is talking a little bit about cold season, but if it is a strong cyclogenesis event, the NAM3K is going to excel within the 24 hours. So, so you can look at the HRF, but also important to look at the individual members as well.
All right, thank you, Tim, for your question. Eric.
Yeah, so with what Rodney was saying, I think that like kind of in that short-term like frame, it's important to make sure that your conceptual models like matching up with deterministic models. So like what you're seeing from the ensembles is the spread of an ensemble system, but what you can really do with that is then correct your conceptual model to come towards a more deterministic solution. So maybe like if like for the sea breeze example, like if sea breeze was late or if it was like it was coming from a different direction, and your moisture is kind of sitting in one area, you can make those kind of fine-tuned adjustments and message that in the short term. And so I think that the deterministic thing, it's important to remember that you're looking for like what supports your conceptual understanding, because that's probably going to be better than what a model generated is going to be showing. Because especially with the popcorn convection, it's really hit or miss.
Yeah, I agree, Eric. That's a good point. And I mean, I think what we see in this last slide here, and where you see the max there, where it's kind of popped up all over the place, is you see the way that the forecaster can approach it is, okay, the max says, here's where I'm at in the probability space as to what's possible, what's on the table today, what can the atmosphere perform, what can it possibly give us? And then through mesoanalysis and some of what Rodney's saying about picking the members that you think excel in this type of scenario, and then the mesoanalysis, you're slowly driving that initial kind of idea as to what's possible. You just don't know where it's going to happen yet, down in scale to when and where it's most likely to happen. And so from a watch to warning time frame, you can and IDSS all the way, you can kind of take that to and use different aspects of this ensemble to help you all the way down to, and obviously now we've got increasingly we're seeing the WAFs and where we can even start to look at things more in the near term and versus an HRF run that may be getting 6, 7, 8, 9, 10 hours old. No, good point.
All right, very good question. Any other questions? I know we're close. It always seems like we're closing on the hour faster than we can imagine. But any other questions or comments? Okay. I'm hearing none. So if there are no more at this time, again, this again is being recorded. So if there's any questions and you come up with anything, you watch it or share it with your staff and they have questions, feel free to forward them and we can get them addressed later on. Again, some kudos in chat. Yes. And so with that, I guess, Justin, Rodney, thank you again for a really great presentation, a lot of really good information as we move into this transition from spring to summer, and this becomes a more prevalent conversational topic in the offices. So if nothing else, a great talk this morning. Thank you for the great information. And we'll get this up on the Eastern Region Science Sharing Google site after sometime later today, or as soon as the recording is ready. And with other than that, I wish everyone a great rest of your Friday and a great weekend for those of you that are off. So thank you.
Thanks a lot, everybody. Happy Easter.
Yes. Happy Easter to all that are celebrating. And happy